So what we're going to do first is a couple of things. It will go online after lecture. But what I've done is, because this is really the only day of review that we're going to have, what I did is I took all the multiple choice from 3 different tests. And you can either sit here right now and just take a look at all the pages with the notes and stuff. What I'm going to do is, I've already got it scanned. I'm going to take it and put it on Blackboard so you can get a clean PDF of it. This is the kind of stuff that'll be on the test for tomorrow. And just so that I can record the video of it so that there is some record of it existing. So you can just, what you can do is just pause the video every couple of seconds. And then, so what I did is I took the last 2 summer tests and a spring test from the year ago, and you can recognize some of the versions. And I don't know where 24 and 25 went. I got it all together. But 73 problems should be fine. So that's going to be online early afternoon. What I've got now is a couple of tests that I've stripped out just the problem sections. And what we're going to do is go over it together. If you have any questions about these topics, probably after the first hour, we'll just start taking requests. Just as an outline, for test 3, there will be an appetizer and then 3 problems, along with the usual 25 multiple choice. Bring your green Scantron. Bring the usual assortment of pens, pencils, erasers, highlighters. The one thing that I won't bring extra copies, or I won't bring extras, but if you want, because it's so easy to make, I mean, if you ran out of paper, you could take a sheet of paper, fold it in half, and use it as a straight edge. But bring your own ruler. So bring just a simple 12-inch, or probably even better, like a 6-inch plastic job, or just the standard ruler. Either one will be fine, because you're going to need that for the for one of the problems. You're either going to get a mirror or a lens. Most likely, I would double practice the virtual, the ones that involve virtual image, because convex with the real image is just so boring. Convex lens. So the other thing that I've noticed is converging mirrors and lens may produce virtual images. Not all of them produce real images. It depends on, the whole thing is based on, is it a converging or diverging object? The diverging objects, the diverging lens, the diverging mirror, will always produce virtual images because they're diverging. Converging, a lot of the time, will produce a real image. But sometimes they don't. And it's all based on the whole order of object, focal length, and then the mirror or the lens. If it goes object, focal length, mirror, lens, most likely it will be virtual. If it's, it'll be real. If it's focal point, object, and then mirror or lens, a lot of the times it is virtual. Appetizer could be Snell's law, could be polarization. And so those are really the topics that we got to cover. For the mirror or the lens, be ready for a two-ray diagram that you're going to have to draw. In my opinion, the ray diagram is important because it allows us as the grader to confirm if you know what you're talking about. If you get a magnification that's -2 and your image is upright and smaller, then we know we got problems. So you've got to make sure that the image is appropriate to that of the mathematical answer. If it doesn't match, I'm not looking, you guys aren't art majors, you guys aren't architecture students, so I'm not looking for perfection. Just get it close enough, show that the rays kind of come together in the right point, and then everything will be fine. Second, single, double slit. The diffraction grading will not be on the test in terms of a problem. It could be in terms of multiple choice. So understand all the values for when M is what, all that fun stuff. The other thing is thin film. And what to do about that. For single and double slit, for thin films, it is critical to know in the index of refraction of the middle material. Technically, I think it would be a better idea if we just memorize, or if we used 2t equals m lambda over n and 2t m plus 1/2 lambda over n. Because if you write it like that always, you'll never forget what n is, or that n could be used. If the soap is the middle material, like a soap bubble, then you use the index of refraction of soap. But if it goes glass, air, glass, n is 1, so effectively the 2t equals m lambda returns. The thing that I've been trying to answer for my existence and my well-being is I've tried to figure out an easy way of associating these things. And so I know that technically even is not the case, but odd, that is appropriate. And you've got constructive interference and destructive interference. And the thing that I memorize, or that I remember, is this. And all of these are, is there a half or nothing added to M? This is, I'm looking for mnemonics. If anybody can come up with a catchy phrase, let me know. But as far as I understand, if you've got an even situation and you want to know about converging, that's a 0. So I'm going to use 2t equals m lambda over n. I know that even destructive, therefore, now uses this. Yes?
Okay, you know for single and double slit how double slit m can be 0, but for single slit it can't?
Yes.
For thin films, how do you know that m can be 0
Good question. This is, okay, I'm gonna get to it. You're on the list. So this is the relationship between whether or not, because there's a way that you can rationalize it out, and I just haven't familiarized myself with it in order to determine this. But what I did is I just memorized a matrix, a 2x2. I go alphabetical, 0, 0 across the diagonal, everything else is a half, and then I've made a cheat sheet that answers everything that I need to know. Now, with minimum thickness, you could have a situation where there is an odd reflection. Let's just say we go from 1, 0 to 1.5 to 1.0. If the new n is greater than the old n, you get a phase shift. If not, there is no phase shift. So with minimum thickness, you can end up in a situation where it's an odd. So constructive is 2t equals m plus 1/2 lambda over n, and destructive is 2t equals m, well, just m over n. If it was a situation where there was, let's make it 0. So it could be 1.0, 1.2, 1.5. So you're always going from one medium to reflecting off a medium where the index is lower. So in this case, it is for constructive 2t equals m lambda over n, and destructive is 2t m plus 1/2 lambda over n. Okay. So we've got this all set up. And now the key part is which m produces a t where t must be greater than 0. So to have a minimum thickness, it has to be the smallest thickness possible. Well, isn't 0 an appropriate thickness? No, it's 0. Then it doesn't really exist. We have a barrier between us of 0 thickness. You can't see it, it doesn't exist, it doesn't make any sense. So the thickness that you get has to be the smallest, but greater than 0. To produce this, in this case, if you've got m plus 1/2, m is allowed to be 0. Because if that's 0, then you got 2t equals lambda over 2n, and then you can get a valid thickness out of it. If this was 0, the thickness would be 0. Zero thicknesses are nonsensical, so that doesn't make any sense. So the m for minimum thickness must be 1. And so that's how you can tell the difference. In situations where there is the 1/2, m equals 0 is allowed. If there is no 1/2, then m equals 0 is not allowed. Minimum thickness is 1. And so that is a great question. So that deals with the thin films. The single double slit, The thing that I've done to not mess with people, just see if you're paying attention. There are quite a few multiple choice questions where you've got a single slit, you got a double slit, put it in water or put it in some fluid, and then tell me how the distances change. In situations like that, and once again, while we'll do this, we'll do a review as we're going. There is single slit, there is double slit, in single slit, it is destructive only, and this is d sine theta equals m lambda. Now, if it is in a material, then you just divide by n. Using the small angle approximation, we get this, and then D equals L, big L, m lambda over n. So this takes into account the index of refraction of the medium. So you can look at this and play games with it. If lambda increases, then the length increases. So understand that if you increase one parameter and hold everything else constant except for one other parameter, how would that change? Another example, if n increases, L decreases. If L decreases, then L must decrease as well. So when you look at all this stuff, you understand the relationships between the two. For double slit, you've got constructive and destructive. For constructive, it's d sine theta equals m lambda over n. Destructive, d sine theta equals m plus 1/2 lambda over n. Now, if it's air, then you can just dump the n's. It doesn't really matter. N is 1. For both cases, m is equal to 0, 1, 2, 3 for both of these. For single slit, m is equal to 1, 2, 3, etc. You go through the same procedure. Sine becomes tangent, tangent becomes this, and you end up with d L over L, m lambda over n. In fact, if I'm being truly accurate, hold on, I'll keep the same form. There was one semester in particular where for single slit, I used big D, and for double slit, I used little d, and the class went nuts because it wasn't like that in the book. In the book, single slit had little d, and double slit had big D. And if you define your variables, it doesn't matter what you use. You could use a slice of pizza and say that slice of pizza, in the case of the single slit, is the slit width. in this case is the distance between slits. And so the whole lesson that I was trying to teach them is that it doesn't really matter what letter you use as long as you identify what that letter is and are content with it. Big D. In the book, fine, we could say it's this. In my opinion, they're kind of interchangeable. As long as you say this is the way it is. Oh yeah, thank you. So, this form, that form, I don't care. As long as you, when you draw the, like for single slit, when you draw your, when you draw your graphic, just draw it like that, and then in the double slit, you still get the same L's. And it depends on, in this case, it was little d, but I'm fine with either one. If you guys want to use that, that's the one that we've been using. I just slipped up and then went in my rant. So understand how all this works out, and because I haven't written the test, most likely I'll write the test tonight and then come in early tomorrow morning and then just print it out, crank it out real fast. The multiple choice is pretty easy to get out. But the thing that I may decide to do, I've done it before on a couple of tests, is to dunk the single or double slit in a vat of water and then see if you pay attention to the fact that the lambda is going to change. Much like you have to pay attention to the lambda in a thin film. And the reason why I do this a lot is because there were a few times in class where I forgot to do the same thing, and it burned my hand severely enough that now I remember it, and I teach you guys to not burn your hand. Remember the lambda in the middle material, and if you're in a tank other than air, there better be an N wandering around in that equation. So let's do some problems. Now what this is, I've taken, what I should do is I should scan this to give you just a condensed version. On Blackboard, I've posted a couple of tests. This is, I've stripped out summer 14, spring 15. Ooh, there's the two missing multiple choice. Hold on. Oh, and it's scrolled off, so it doesn't really matter. Inverted and enlarged. Okay. So for something like this, spring 15, I'm about to shut that door. And then this is summer of 15, and then this is summer of 16. So I got 4 tests here. A lot of them are very similar. So what I'm going to do, that'll be the first test we'll work on. Unlock and shut that door. All right, now, Appetizer 1, and as we go through these, we can, on the first pass, I won't do, in my opinion, repetitive problems. There's sometimes I get a problem, like appetizer from summer 14 looks a lot like appetizer problem from July of 15. So we'll go through it once, and then once I go through all the problems that I know we've talked about everything, then we can go back and talk about this stuff. Light passes through two polarizers. The axis of the second one is 30 degrees with respect to the axis of the first polarizer. So the first polarizer is like this, second polarizer is like that. That's the vertical, and then that is theta, and then the theta is 30 degrees. If the intensity of the light after it passes through the second polarizer is 2 watts per meter squared, so that is I2, this will be I1, that will be I0. What is the original intensity of the unpolarized light before it passes through the first filter? So the question is, what is I0? According to the rules of polarization, I1 is I0 over 2. So if you send unpolarized light through one filter, the intensity gets cut in half.
Does it matter the angle of the polarizer?
No, not really. What does matter is the angle of the polarizer from this one to that one.
For polarized light.
For polarized light. The orientation of the first polarizer doesn't matter.
So if it was at 30 degrees, you wouldn't calculate it?
If I said that this was 30 degrees and that was 30 degrees,
Or what if there's just one?
what if there's just one? It doesn't matter what the orientation is. What does matter is if there's just one, is it polarized light or not? If it's unpolarized, it's that. In this case, the light hitting is polarized. So you have to use the angle of it, and in this case it's I2 equals I1 cosine squared theta. So I2 becomes I0 over 2 cosine squared theta. I have I2, I have theta. Solve for I0. 2I2, and in this particular equation, you should be able to solve for any of the variables. I can ask for any of that. 2I2 over cosine squared theta, 2 cosine squared of 30 degrees. So it's 4 divided by cosine of 30 degrees. And I get, oh wait, I didn't do that. .33 watts per meter squared. And so that's a simple appetizer problem. In problem 1, ooh, this is, yeah. In problem 1, we have two rays of light from air to a layer of oil, and then it reflects off glass. So it goes from low to higher. Light of wavelengths 720 and 1680 nanometers, and these are the wavelengths that they have in air, both destructively interfere, i.e. they're dark. What is the thickness of the oil? What is the frequency and wavelength of the 720 nanometer in light as it's passing through the oil. So it's just an extra question. Love these problems. So in this case, we're not asking for the minimum thickness. We're looking for, well, in a way it is, the minimum thickness where both of those lights destructively interfere. It starts off at light, or air, 1.0. And then it hits oil, 1.2. And then it reflects off glass, 1.33. So the first ray of light goes from low to high. There is a phase shift. That one goes from low to high as well. That phase shifts. We're dealing with even, and we're dealing with even destructive. So even destructive means that I have 2t equals m plus 1/2 lambda over n. And what I'm going to do is I'm going to say m1 and lambda 1. The other one is 2t equals m2 plus 1/2 lambda 2 over n. So we have both of these. Now when you're looking at this, you know the index of refraction of the middle material, oil. You know what your lambdas are, 720 and 1680, but you don't know thickness, you don't know M1, you don't know M2. You've got 3 unknowns with 2 equations. How do we fix this? Well, for something like this, we haven't dealt with a problem like this, like in 213. Yes?
So do you have to tell us whether it's constructive or destructive?
Yes.
Okay.
What I'm going to do, yeah, and let me preface it with constructive and destructive. I'll either say constructive or destructive, or I'll say bright or dark. If it's dark, then it's destructive. If it's bright, it's constructive. Those are the word associations. But the type of interference, I will give that to you.
Thank you.
It will be stated, yes. To get this, this is a unique type of problem. This is a problem where technically there isn't enough information, but we're going to use your faith in me not being a jerk. What you're going to do is you're going to set these two to each other. And just so you know, if they do this during a test, I'm going to go upstairs, I'm going to pull that hammer out of the person who's hitting the walls, and I'm going to hit him with it and see if he likes it. And heaven help him if he does it during the final. I know. And actually, if you want, tomorrow, if he does this during the test, we can all go up there and take turns hitting him with the hammer. So you set the two T's equal to each other and you get this. Well, one of the things that you notice, and in some respects, it's not technically, well, it is kind of useful later, but the ends cancel. No.
It's 2t.
Well, if I divide both by 2, if I had 2t, if I pulled the 2 down and set them equal to each other, okay, fine, I'll do what you want.
Will it still cancel? I guess?
Yeah, they still cancel. It doesn't really. So.
What would N be if it didn't cancel? Like,
In this particular case, in both constructive and destructive situations, they do cancel. And the reason why I had to give the N of the middle material is because the second question, I asked for the wavelength of the light in the material. Had had I eliminated that particular question, I would not have to give you the index of refraction of the middle material. In fact, I could be a jerk and just say an index of refraction of unknown value. And then when you come up and go, but you didn't give us the value, you told us we have to pay attention to the index. And I go, yeah, I didn't give it to you. And then I start cackling, which means that you don't need it. For the first problem, the index of refraction is unnecessary. So you're left with this. And I'm going to divide both sides by lambda 1. And then subtract a 1/2. With problems like this, it's my responsibility to make sure these numbers work. What's the one thing that we know about M1 and M2? They're both integers. In fact, some of them could be 0. I don't think it will be 0, but what we'll do is we'll make a chart. M2, what we're going to do, I know for a fact that M2 is an integer. Oh. Y'all were looking at me like I was just, everything was fine. So M2 has to be an integer, M1 has to be an integer. So what we're going to do to find the minimum thickness is we're going to find the set of integers, or we're going to find the M2 that makes an integer of M1. So for 0, it is hold on. I'm not going to talk to them on the side.
As in like one without one half of That's the only thing I struck in whenever I didn't know someone to use. That's what we're doing.
So did you guys plug in numbers? None of you? I was gone for 5 minutes. You could have solved this. The what? Yeah, let's do that. So in this experiment, what we're going to do is anything associated with lambda 1 has the relationship that it has in M1. So lambda 1 in this case, and you could pick either one, is 720. Lambda 2 is 1680. So anything associated with 2, M2 and lambda 2 is 1680. So, and it could be either one. You don't have to pick. You could say lambda 1 is 1680, it doesn't matter. But once you made a pick, stick with it. So if M2 is 0, it's 1680 over 720, 0 plus 1/2 minus 1/2. And that gives me an M1 of 2/3. So M2 is not 0. Now we use M2 is equal to 1. And what I get is 5/2, 5.5. Now the thing that I'm going to have to make sure of is that these numbers do not get crazy. This is an older test. Whoa, hold on. 1680 divided by 720. Oh, I do have faith in myself. All right, times what? Oh, I know what I did. Yes. So that checks out. M2 in this case is 1. M1 in this case is 3. Now, had you switched and said that M2 and lambda, or I'm sorry, if you said lambda 1 was initially 1680 and lambda 2 was 720, what would happen is that you would go through this and M2 would be 3 and M1 would be 1. What I promise on the test, I will try to keep the M values either 0, 1, 2, or 3. Just so it would be incredibly rude on my part to have it. Well, obviously, M1 is 75 and M2 is 308. Have fun, kids. Now, you could do it if you had a spreadsheet or could program, but since we're only doing this with pen and paper and a calculator, we're going to keep it simple. So the values that I give you for M, it's my responsibility to make sure that the M values are kept to a reasonable level. So I could say values of 0, 1, 2, and 3 are all on the board. Anything greater than 3, I'd be like, oh, come on, it's just wasting my time. And your time especially. Question, what's the thickness? Now, pick one of the equations, 2t. Oh, in fact, actually, for this you do have, if I asked only for those values, you don't need lambda or index of refraction. But for the thickness, you do. So thickness is lambda 1 over 2n M1 plus 1/2, and you get this. So lambda 1 is 720 over 2 times 1.2. M1 is 3, and that gives me 721.5 nanometers. I'll probably keep the answers all in nanometers just for, I mean, it's a good optical distance. The last question is, what is the wavelength of the light as it's passing into the oil? So the new wavelength is the air vacuum wavelength divided by N. So this is 720 divided by 1.2. And that gives me 600 nanometers.
That last one I asked?
What?
What did it ask for? The wavelength?
I asked for the wavelength of the 720 nanometer light in oil. And one of the things in these tests that I found as a problem, I will try to make certain that it is explicitly stated that if lambda was 720, it's either 720 in air or it is 720 in whatever substance it is in, and it will be specifically stated. I'll try to stay away from, you've got light, it's 720 nanometers, and I don't specify if it's in vacuum or water or in some medium. Yes?
Could you just explain why you couldn't set M2 equal to 0?
Why I couldn't set M2 is equal to 0?
So like it never be 0.
M2, well, in this particular style of problem, if I plugged in M2 of 0, M1 must be 2/3. And if M1 is 2/3, that's nonsensical because the indices that we're using are all integers.
Okay, so if M1 somehow equaled 1, could you still use 0?
Yes.
Okay.
And in fact, it can be used because we're using M1 plus 1/2.
Gotcha.
So M is a value, or is a potentially useful.
So you just have to have two whole numbers.
Mm-hmm.
Okay. Thank you.
Yeah.
1050 for me.
What?
It missed 1050.
Did I get the thickness? Oh, it's because I'm, fruitcake. All right. All right. Dial it back, Vance. $10.50. And there we go. All right, that is problem 1. Problem 2 on this test from the summer of 14. I have a mirror. Oh my goodness. Here we go. All right, this is a more fun problem. And it helps to just sit here and read it. I have a mirror. The image is 4.8 centimeters to the right of the mirror. So it's a mirror, and if the image is to the right, that means that the image distance is negative 4.8 centimeters. Images to the right of mirrors are negative image distance. In the way that we've been doing 214, you always have the initial object to the left of the mirror. The reflective part of the mirror is to the left. So you can't have an object to the right of the mirror because that would be crazy. And if you have an image to the right of the mirror, the image is virtual. So we're dealing with a virtual image and an image that is to the right. Object is 8 centimeters to the left of the mirror. Oh goodness, this is a good problem. Object distance is 8. The image is upright. It is virtual and to the right, and the magnification magnitude, in fact, since it's upright, we can add it in right now. The magnification is 0.6. What is the focal length of the mirror? Include sign. Is the mirror convex or concave? The thing that we need is the focal length. 1 over f is equal to 1 over o plus 1 over I. That means that the focal length is 1 over o plus 1 over I inverted. The object distance is 8. The image distance is 4.8. That means that my focal length is, and once again, now that I've made a couple of math errors, you guys need to watch me. And I get negative 12 centimeters. So since this is a mirror with the focal length of negative 12, it is a diverging mirror. Mirrors with negative focal, or anything with a negative focal length is diverging. Yes.
Where did that negative come from?
Which negative?
The O minus I.
Because the image is to right of mirror, the image distance is less than 0. Because images to the right of mirrors are negative. Images to the left of lenses are negative. It's a diverging mirror, so it is a convex mirror. convex mirrors are divergent. Now I want a three-ray diagram. Let's get this right. O is equal to 8, I is equal to negative 4.8, magnification positive 0.6, focal length of negative 12. All right, that's the first part. I need to get my colors ready. All right. In the test, you're only expected to draw 2 rays. The purpose of this is just to confirm that you know how to draw a ray diagram and accurately represent the image.
Do you want us to bring graphing paper?
I will bring graphing paper. In fact, what I'll do is I'll take one of these sheets and Xerox it and make like 100 copies so that, yeah. Now I got to choose where my stuff goes. Object is obviously to the left at 8. That's focal length is over here at 12. I'm gonna put my wall, I'm gonna do a block per centimeter. Keep things consistent. So the focal length is negative 12. This is a convex mirror, so 1, 2, 3, 4, 5, 6, hold on. 3, 6, 9, and 12. F prime, 3, 6, 9, 12. May be handy. Object distance is 8. 4, 8. Image distance is negative 4.8. 2, 4, 8. Now the image is smaller. So what we're going to do is we're going to take, we're going to draw a 5-block object. 2, 4, 5. Draw it like that. The image is 3/5 of this. And so then we get that. All right, first ray, easy ray.
Quick question.
Yes.
So when you're drawing your object, say you made it 5 blocks tall, would you just multiply 5 by 0.6? And that's how many
Which
blocks
gives me
it's
3,
long?
yeah. If I chose something odd and said I picked 13, I would still multiply by 0.6. The reason why I know I have a magnification of 0.6, so I know the math is easy. So I was leaning between either 5 or 10 blocks, because then I know my image is either 3 or 6. And by using graph paper, I can get a little bit more of an accurate height. It's an entirely practical matter. The first ray, the easy ray, probably the ray that you first go after, is straight at the middle, and then it reflects like this, and then the ray that I'm interested in is the virtual dotted ray, like this. You don't have to do the continuation of that, but those two I really want, and this one. The second ray starts parallel, and what happens, it is a convex mirror, so the ray gets diverged away, and then we trace it back to that. And that would be good enough for a test. On the test, and if it showed up on a final, that would be just as good. Yes?
Will you kind of explain like how, you know, how far up you draw the object and the
I don't usually give specific heights. So it's a personal and practical choice. If the magnitude of m is greater than 1, I draw the image as the biggest construct. I don't know. Draw the image as the biggest. If m or m is less than 1, I draw the object as the biggest. So really, I'm only interested in the actual ratio of the image and the object heights. And
sorry.
go. So what I do is I look at the magnification. In this case, it's 0.6. So I know that for practical purposes, I'm going to make the object has to be the bigger of the two. So I'm going to draw a big object because I know I'm going to get a smaller image. If the magnification was like 6, I'm not going to draw a 5-block object because I'm going to get a 30-block image. But what I am going to do is I'm going to draw like an 8-block image because I know that I'm going to get an 8/6 block object. So it's you need to look at the magnification, and if it's less than 1, pick the object as the bigger one. If it's reversed, then pick the image. Now, as to what height you pick, I pick heights that the smaller the object in this particular case, the smaller the image is going to be in a big deal. So if they're so small, I don't think you'd be able to, in my opinion, it gets more difficult to draw it. If you've got big objects, you can line it up and there's a little bit of forgiveness in my opinion. But for itty bitty stuff, it gets harder. So it's a personal choice.
So when do you have one arrow going up and one arrow goes down? Because I saw in the notes, I think it was inverted, but I don't.
All of my objects, there may have been a weird example somewhere where I started the object inverted. I mean, this is 214. So I have to keep things simple. If we were doing upper division optics, then I could get strained. I will always put the object to the left initially. The object will always be upright. The image can be inverted or upright. It has a choice. In this case, it so happened to be that it was upright. There may be a case where it's inverted. And the thing that you can tell is, that's why it's so important to get the numbers. If the moment I saw that I gave a magnification of 0.6, I know reduced and upright. I know it's to the right, so I know it's virtual, so I know I got dotted lines coming to it. The last one, the tricky one, is a ray that, since it is virtual, becomes parallel and reflects away like that. And so what you do, this is just for thoroughness, is you aim at that focal point and you draw the ray like that. Becomes parallel. Through the middle. And so those are the three rays. Some people like to draw the third ray as the second ray, whatever. I mean, it's your choice. But if you do the second and third ray and just leave the first ray out of it, wow, that shows confidence. But I use the first ray to just kind of lock things down and get an idea that, yeah, this thing's going to work. And so there we go. A lot of the variations have been done on that optics handout, and so you can look at it all. Probably I would do, I like the idea of testing you guys, since it's most likely going to be the only time on a test or a final that I give you guys a lens or a mirror, that the resulting image, I'll probably make it virtual, just to make it somewhat of a challenge. But that's the problem. All right, the last one is a really good problem. Summer of 14. That was a good year for a test. You have a double slit experiment on the table. Dr. Eschenberg is your lab partner. He's drawn this picture of the setup and counted the total number of bright and dark bands within a certain distance of the screen. How many total bands, bright and dark, did he count? Now, first off, there's no mention of the index of refraction in this particular construct, which means that all the equations that we use will not involve the index of refraction, because the index of refraction is 1, so we can just set it apart. For bright, it is, I wrote little d in this. I think this was the year I fought my class. D sine theta is equal to m lambda, and then dark is d sine theta m plus 1/2 lambda. D tan theta m lambda d tan theta m plus 1/2 lambda. dl over big L is equal to m lambda. dl over big L is m plus 1/2 lambda. So this becomes simply dl over L lambda equals m. This becomes dl over L lambda m plus 1/2. Now all of these, this is m for bright, this is m for dark, this is dl over m lambda minus 1/2 is equal to m dark, or this is m bright minus 1/2 is equal to m dark. So that's just the math getting to this point. So all I really have to do is find the M of bright, subtract a half from it, and then I got dark. So little d in this case is 0.4 millimeters, or 0.4 times 10 to the negative 3. The L in this case, and people were always just fighting me over this. If this distance is 8 millimeters, and I clearly stated it as L, and that distance is 8 millimeters, and that's also listed as L, the L that you plug in is just 8 times 10 to the negative 3. We're going to get to the total bands later. All I knew is that from the center out was 8 millimeters, from the center out was 8 millimeters. This distance associated it with L. Once I find the M's on one side or the M's on the other. It's not a big deal. Big L is 1 meter. Lambda is 590 times 10 to the negative 9, and that gives me, please let the numbers be gentle, oh my goodness, really? It's that big? Okay, whatever. It's not like the thin film where you've got these and you gotta have numbers that are that behave. So I got a 54.23 in terms of the M bright. That means that M dark is 54.23 minus 0.5. or 53.7. Now comes the point at which you round down because you can't have partial bands. So this becomes 54, that becomes 53, and we get this.
This would be 590 or 590 wavelength.
It's 590 nanometers. So I used 590 times 10 to the negative 9. That did the conversion.
590. Shouldn't there be one more dark band than bright bands?
Hold on, we're about to get to this. First of all, have you checked my math? Okay, she nods her head. Did I get the math right?
Yes.
Okay, good.
I'll be safe.
All right, hold on. We're having competition here. Who else agrees that I got 54.23? You didn't get it? What did you get?
That's what I got.
Huh?
5.4.
Just gonna
Oh, dang it, hold on. 0.4 millimeters is 4 negative 4. 4 times 10 to the negative 4. 8 millimeters is 8 10 to the negative 3. Divided by 590. Hold on. Oh, dang it. That makes this better. Because the thing, also, here's another thing that I was trying to remember in how, first off, all right, we're all seated down. I was wrong. You were right. I know. It's hard to admit that. That's good. That's what we do in all types of big projects, is everybody's looking over everybody's shoulder looking for mistakes. So 5.4, that's a much reasonable number, or more reasonable. So this becomes 5.4 or 5. The dark becomes 5.4 minus 0.5, which is 4.9, which then becomes 4. Now, one of the reasons why I was trying to remember, back in the old days, I really didn't care about the number of bands in terms of being big or small. However, there was a point in time, and I was trying to figure if it happened in the summer of 2014, I wanted the numbers to be small enough that you could draw this thing out. Because my bright is 5 and my dark is 4, this is 0, 1, 2, 3, 4, and 5. This is 0, 1, 2, 3, and 4. And there is no fifth, or m equals 5 indice for a dark band. 2, 3, 4, and 5. I would go insane if I had to draw 54 peaks in this thing. So we go 0, 1, 2, 3, and 4. Now when you're looking at this, the line, the 6 millimeter, or I'm sorry, the 8 millimeter line falls just to the left of the m equals 5 minima, or just outside. So that's why 8 millimeters to the left, 8 millimeters to the right. The question is, how many bands are there in totality going for that 16 millimeter range? And so you could literally count it out. You got 5, 10, plus 11. So there's 21. However, if we do this, the number of bright equals m bright times 2 plus 1. Should be 18? Hold on. The number of dark should be... Thank you. Now I'm right, you're wrong. There's balance, a very Zen thing, yes. So in this case, it's MD plus 1 times 2. So 4 plus 1 times 2, or 10. Total 21. Or you could physically count it out. What I'm going to do if I assign a problem like this, I'll have it such that it can be assigned. Yes?
So you could have the same number of dark as the same number of light.
You will never have the same number of bright and dark bands. Why is that? Because one will always be even and the other one will always be positive.
As long as they're L's.
Their L's, theirs could be different. They can have, in this case, their M's were different.
The L's.
What do you mean? Oh, the L's, yes.
Okay.
The distance from the central band out for both bright and dark will be the same. That's why you always have to round down. Yes?
What would you do different if this whole problem was in Liquid Rebellion?
Liquid, ooh, good question. If it was in Liquid Rebellion, there would be an in there and there to start out with, which means that there would be an in here and an in there. And then whatever that index of refraction is, you would put it, yes. Why would they cancel out? Okay. You got probably getting, once you caught me in a bad mistake, now you're just all going insane with power. Is that it? I think that is. No, it's fine. I respect that. You're answering now with a little bit of insolence. I like that. Now, just make sure that you're right when you try to correct me. Unlike what you've done the last 2 times. So, all right, so that's 2014 summer test. What I'm gonna do is I'm gonna start going through these things. Problem 1 from the spring of 15, we're gonna worry about that on Wednesday because that's for a final. The appetizer problem is legit. It could be on the test, I don't know. But let me tell you what's frustrating about it, because I put in a little bit of a bomb inside to see if you were paying attention. Oil has a higher index of refraction. I'm looking for, oh goodness, I have to find it somewhere. Since I don't have the number with me, I'm going to declare that the N of oil is like 1.2. Whatever it is. I gave the number on the second page of the book. Let's see, spring 15? I don't think I have that with me. Ooh, I do have spring 215. Oil, 1.2, lucky guess. All right. So the index of refraction is 1.2. Which one doesn't have a critical angle? Now let's say for a moment that's where the bomb is. Snell's law is N1 sine theta 1 equals N2 sine theta 2. And we'll just have generic boundaries. I'm not interested at the moment as to which one's air and which one's oil. For critical angle, that one would be theta c and that one would be 90 degrees. So sine theta 1 becomes 1 because sine of 90 is 1. And we're left with N2 sine theta 2. So N1 over N2 is equal to sine theta 2. So theta 2, which in this case would be the critical angle, is the inverse sine of N1 over N2. So this is sine theta 1, N1. Now in this case, what I'm going to do is I'm going to say that N1 is oil and N2 is air. So N1 or actually, hold on, the way that I have this set up. Sine theta 1 is the one with the angle that's 90 degrees. So for if it was to do this, that's the setup. So N1 is 1, N2 is 1.2, and that gives me a critical angle of 56.4 degrees. Now in this particular arrangement, it's the oil which has the 90 degrees. So in this case, it will be the oil as the one term and the air as the second term. if we were to do this, we would have sine of inverse 1.2 divided by 1. And what we get is that the computer gunks up. So the answer for this, if it's passing from ray A is the one on the left, ray B is the one on the right. No, I don't have them labeled. I think one of the questions that they asked was, which is A and which one's B? In the case where it's going from air to oil, there is no answer. You just say this doesn't happen, it's impossible. For the one where it's going from oil to air, you do get an answer, it's 56.4. So a lot of people came to me during the test and went, are you serious about this? It doesn't work. I'm like, well, sometimes the answer is it doesn't work. So I think it's been this type of problem is very common to have something where it doesn't work because I've explained it so well about why can you have a critical angle from higher to lower index of refraction, but lower to higher doesn't happen. Okay.
So it doesn't ever refract, or it doesn't ever reflect?
It doesn't.
It's going from air.
Well, I think you could probably, I mean, you could do it all mathematically with Snell's law and see what happens. But the answer is that you could never get an angle that when it refracts is 90 degrees if you're going from lower to higher. Because what happens is that for a low to high, it will always curve less than what something like this. So the incoming light, basically what will happen is the incoming light will hit 90 degrees before the exit or the refracting light hits 90. It's physically impossible because the steeper, the greater, I mean, granted, it's true. Theta R in this case, if you're going from lower to high, or I'm sorry, from lower to higher, the angle of refraction will always be less than the angle of incidence. It's just the way that the math is set up. So you can never produce an incident angle that would produce a refracted angle of 90 degrees because that refracted angle is always less than the incident angle. So it's numerically impossible as theta I goes from 0 to 90 to get a theta sub R that's 90 degrees. It's numerically impossible. And so that is the answer for that. This was the year where oh no, I could do, all right, never mind. Problem 2 is like the one before. Problem 3 is a little bit different. It's destructive. Low to high, it does change. High to low, it doesn't. So we're dealing with an odd destructive. So odd destructive means 2t equals m lambda over n. Always remember the index of refraction, particularly because we're dealing with soap. So t is equal to m lambda over 2n. It specifically asks for the minimum thickness. Now in this particular case, since you're the one who keeps asking about this, Is my M value 0 or 1 to produce the minimum thickness? Which one can it be?
One.
Exactly, why? And you said it with confidence, so I have to respect that. That's fine. Why can I not use M equals 0 for this?
Because it has to be the minimum thickness greater than 0.
Correct.
0 makes the whole thing 0.
In this particular equation, if M was 0, the thickness would be 0, and you can't have a 0 thickness and still have thickness. It's just can't do that. So M has to be 1, lambda is 650, index is 1.4. Wow, this was an easy problem. You guys would love this. So 325 divided by 232 nanometers. So that's it for that. Wow, I went easy on them that spring. Trying to think, why would I be? Oh, it may have been a combination of the fact that I did compound lens and then this guy in there. Okay. So that's spring 15. Appetizer problem. Let's just address it, the setup, or we'll run through it real quick. I want to know theta such that the exiting intensity is 29% of the original. So I1 is equal to I0 over 2. The initial light is unpolarized. That was specifically stated. So I2, which is I1 cosine squared theta, is I0 over 2 cosine squared theta. I want to know what my theta is. So 2I2 over I1 is equal to cosine squared theta. Square root of 2I2 over I1 is equal to cosine theta. What's going on? Oh, thank you. I know it. There you go. And remember, that's I0, that's I1, that's I2. So I get this, which means the square root of 2I2 over I0 inverse cosine of all that is theta. And I get that. This becomes cosine minus 1 of the square root of 2 times I2 over I0 is 0.29. And that gives me .4 degrees. And so that's my theta. Effectively, I took this core equation in a previous test problem I solved for I2. Or no, I solved for I0. In this particular case, I solved for theta. The next problem is, I'm just gonna get the focal length and describe it, and then we'll skip the ray diagrams. Object is always to the left of the optical object. That seems to confuse a lot of people. The object distance is 20. The magnification is -2. The first question, I want to know F and I want to know I. This is very similar to the problem in problem set 8, where you've got like the mystery lens. The two equations that we have are 1 over F plus 1 equals 1 over I plus 1 over O, and M is equal to -I over O. I have O and I have M, I can solve for I. So I is equal to negative MO. So this is negative of a -2, O is 20, so my image distance is +40. And the real question is, am I dealing with an image or am I dealing with a mirror or a lens? Given M and O, what is the focal length I? Is it concave? Oh, there it is, right there in the middle. Mirror. Because I think in the end I looked at it and went, I think they need to know if it's a mirror or a lens. So now that I know that it's a mirror, I've got an image distance of +40. The F is 1 over I plus 1 over O inverted. So the image distance is +40. The object distance is 20. And I get positive 13.33 centimeters, or 13.3. Now the ray diagram, you guys can handle that later, but the focal length is positive and it is a mirror. So when the focal length is greater than 0 and a mirror, it's concave, and it's a converging mirror. So I've answered what F is, what I is the object concave or convex? It is concave. Is it real? Yes, the image distance is positive. Is it upright? No, it is negative magnification, so it's inverted. Is it enlarged or reduced? It's enlarged because it is magnitude greater than 1. What's the focal length, positive, negative diopters? This becomes, in diopters, is 1 over 0.1333. Because a diopter is an inverse meter, so it is positive 7.5 diopters. And that's for the lens. Or, I'm sorry, that's for the mirror. Problem 2 we've done, problem 3 we've done before. Moving on to the last test, we'll probably see that this is all done before. God, I'm so repetitive. In the last test, problem 1 we've done like all the others. Problem 2 is, oh God, it keeps showing up. 2 and 3 are repeats of earlier ones. This is the one that you talked about. It's in Liquid Rebellion. So you would have that in wandering around. The only one that's a little bit different than the others is the appetizer problem, and that is you have vertically polarized light hitting one plate where the angle is 30 degrees, and then you had another plate where that angle is 60 degrees. So this is I0, I1, and I2. And I specifically said that the initial light was vertically polarized. So I1 is equal to I0 cosine squared theta and I2 is equal to I1 cosine squared theta 2. Now theta 1 and theta 2, this one is theta 1. What we're looking for is that the theta 1 and the theta 2 is the change in angle. The initial theta here is 0. So that theta 1 is 30 degrees. To go from there to there, it goes from 30 to 60. A lot of this is like that demo that I did in class last week. It's not about the complete change in angle. It's about the change in angle from stage to stage. The first stage went from vertical to 30 degrees. That's 30. This one goes from 30 to 60. That's 30 again. So I2 is equal to cosine squared theta 2 times I0 cosine squared theta 1. So this is cosine squared 30. And I want initial over final. Or I'm sorry, final over initial. So there's one extra stage. So what I'm looking for is I2 over I0 cosine squared theta 2 cosine squared theta 1. This leaves me with cosine squared 30 times cosine squared of 30. Or cosine of 30 to the, I forget what you do after cube, square it, cube it, whatever the next one is. Cosine 30, and then put it to the fourth, and you get 0.5625. And then that's the answer for that. That's all the time that we have. I will post this video online shortly. The thing that we need to remember, I gotta go off campus from 1 to probably 3:30. I will try to get back from 3:30 to 5 so that I could talk if you guys want office hours. All right, that is it.
A quick question, will there be anything with compound?
No, there will not be compound lens problems on the test. On the final, yes.